So looking at 3.1.2, the Chinese double guess, you can read through a little bit of the background context here, right? But it's another method that we use to solve equations of varying degrees of difficulty. Some of them are easier than others. So I'll take you through an example here, but the process behind it really is kind of along the lines of what we did in the Egyptian cases. Right? We would make a guess, right, if we were using false position. It's really just kind of like the double false position, but it's what we do with it afterwards that's going to make it unique. So we make two guesses. We run through with those two guesses. So looking at this example here, it's a familiar looking problem. X plus x over 7 is equal to 24. I'm going to make a guess that I'll call G1, guess equals G1, G for guess, and guess 2. I'm going to run that through the left-hand side. All right, so this part of the equation, I'm going to run through with whatever my guess is. And how that differs from what it should be equal to, the 24, is going to lead to an error, the amount of error, all right? So if you're more algebraic minded, what's happening here is, and I'll just kind of do this off on the side, you got x plus x over 7 is equal to 24. If I were to subtract the x and the x over 7 from both sides, I would get 0 is equal to 24 minus x over 7, all right? Or I could even write 0 is equal to 24 minus x plus x over 7. Either way really amounts to the same thing. Let me just smidge this up a little bit. But what's happening here is we're trying to establish a case where whatever we put in for x here and here will lead to this expression, which when subtracted from 24 should be equal to 0, all right? Meaning that there is no difference between what I would have come up with and what I should have come up with, all right? So that's kind of like the heart of what we're about to do here. So I would then plug in a guess, and we learned from the Egyptian false guess, all right? So we'll just kind of go back to it. False position, sorry. The guess in false position relied on, where is it? Choosing a value that was convenient for the most complicated part of the equation. All right, and that would be the fraction in this case. So we're going to do that here. It's just we're going to do it twice. So the first convenient value I can think of is 7. Another one would be 14. Any multiple of 7. I'll do something bigger. But let's see, what do they use? I'll use something other. They use 14, so I'll go to the next one, which would be 21. All right. So 7 plus 7 over 7 is going to be equal to 7 plus 1, which is 8. All right. From that, so my E1 is going to be whatever I got from G1 evaluated into the function. So that would be the left-hand side, which I think we abbreviate in the notes as LHS. Left-hand side minus the right-hand side, which was 24. So right-hand side. Left-hand side gave me an 8. The right-hand side gave me a 24. So my E1 is going to be negative 16. All right. Here, for my, and I'll abbreviate this, we'll just call it LHS up here, so for a little consistency. My left-hand side is going to be 21 plus 21 over 7, which is 21 plus 3, which is 24. So my second error would be 24 minus 24. Now, as a consequence of this, you see the error that I got of 0 means that there is no difference between what I put in as my guess and so the answer that I got when I put in my guess and the correct answer, which actually means that my guess is correct. All right, so I stumbled onto the correct answer. So if you recognize that, great. Then you could stop. All right, there's no penalty for stumbling onto the correct answer. That being said, there's no guarantee that that correct answer is going to be a nice, neat number that happens also to be a multiple of 7. So there is that. And also, there's a possibility that maybe you don't recognize that you stumbled on the right answer and you're just following the algorithm. All right, so I'm just going to continue going with that. So x is equal to your first error times your second guess minus your second error times your first guess over the difference of the two errors. I'll rewrite it here, but it's E1 G2 minus E2 G1. There's a little distributive property at work here. Sort of kind of like a weighted system. You're trying to figure out, again, it's a sort of a scale factor kind of idea, but we'll just focus on the algorithm for now. So I get negative 16 is my E1. My G2, I'll use a highlighter here. I'll just highlight the relevant parts. And my E2, which happens to be 0, so it's going to 0 out, and my G1. All right. So 16 times 21 minus 0 times 7 over negative 16 minus 0, which amounts to negative 16 times 21, because 0 times anything is 0, over negative 16. The negative 16s would actually cancel out and leave you with just a 21. So eventually I would get to the 21, even if I didn't recognize that I stumbled onto it by making that guess, right? But there's no, like, for example, in the choices that were in the solution here, it was, the guesses were 35 and 14. Those guesses were with the idea in mind that, all right, author of the question, I know that the answer is 21, so I don't want to make that my guess. But if you were doing this for real, you don't know what the answer is, so you guess what you guess, and then hope for the best. So there you go. All right, so that is really the solution there. Same idea here. The guesses that they chose were 12 and 18, because knowing that the answer was 9, actually that would be one of my first guesses. I would take 3, because we'd be looking at multiples of 3, because whatever that denominator is, those are going to be our good values. So I would choose any multiple of 3. I would start with 3, then maybe I would go to 6. Right, 6 would be fine, but I might select 9. I might select 3 and 9, or 6 and 9, or whatever. In this case, I'll choose 3 and 6. That's what I believe I said first, so that's what I would go with. All right, so G1 would be 3, G2 would be 6. All right, if I plug in a 3, so 4 times 3 minus 2 times 3 over 3, which is really just 2. That's the whole point of selecting that number. All right, so E1 would be 10 minus 30, which is negative 20. All right, so I would plug in my 3, all right, for x. Now, x is in 2 places here, so I'd make sure to be careful about that. Then I would do my second guess, which was 6. And I get 20. All right, so my E2 would be 20 minus the 30, whatever the right-hand side is going to be negative 10. All right, so x is going to be equal to negative 20 times 6 minus negative 10 times 3, oops, jumping the gun there a little bit, over negative 20 minus negative 10. All right, so that's negative 120 plus 30 over, two negatives make a positive, so negative 10. So negative 120 plus 30 is negative 90. Divided by negative 10 is equal to 9, and that happens to be the correct answer. All right. It works the same way if you have 3 terms. Again, just like with the Egyptian false position, if you have multiple fractions, you want to make sure that you account for each of those denominators. So not the case in example 3, but in example 4, we would want to make sure we're careful about that. All right. In 3, again, choose what you deem to be the most convenient values. So I'm going to say G1 is 5 and G2 is 10. Just choosing something different from the printed examples. All right. My E1 is whatever I get on the left-hand side if I plug a 5 in. Plug a 5 in. So 4 times 5 plus, use the calculator if you want. There's nothing wrong with that. But if you can do it in your head, that's good too. I mean, both ways. All right, do it in your head and then check it with a calculator. So 28, and I'm going to subtract off the 70 from that. All right, again, the right-hand side. So 28 minus 70 is what, negative 42? Oops, I got to get an answer in there. Yeah. All right, so go back and replace each of the 5s, each of the 5s that we subbed in with a 10. I mean, you can combine like terms before you even get started because 4x plus 1x is 5. You could do that. Right? So a bunch of different approaches. E2 is going to be 56 minus 70, which is going to be negative 14. All right. So x is going to be negative 42 times 10 minus negative 14 times 5 over negative 42 minus negative 14. So that's going to be negative 420 plus 70. All right, 2 negatives make a positive. All right, negative 42 plus 14 is negative 28. I'm going to have to go to a calculator at some point anyway, so I'll double check all this. So we're looking at negative 350 divided by negative 28. Both are divisible top and bottom, right? So I can divide top and bottom by negative 7. So that gives me 50 over 4, all right, which is 25 over 2, which is 12.5. So like I said, I'm going to check it with the calculator anyway. So did a little stretching mentally. See if I can figure it out in my head before resorting to a calculator. But you're doing this on a test. You're doing it quiz, anything like that. Why take the chance, right? So you type it in, you get the 12.5. Right? They use different numbers, 15 and 20. I use 5 and 10. As long as they're convenient values, then you pretty much can't go wrong. All right. Same idea for the next one, except this time I need a value that is a multiple of both 6 and 3. Right? If it's a multiple of 6, it's also a multiple of 3. So my guess 1, they use 6 and 18, so I'll use 12 and 24. All right. If they're not similar type denominators, like 3, the multiples of 3 are part of the set of the multiples of 6. So, like if you pick a multiple of 6, you're good. It's not the case if this was denominator of 7 and 6. So a little different conversation there, right? So my E1 is going to be 8 times 12 minus the fraction of 2 times 12 over 3 plus the fraction 12 over 6. All right, so I get a 90 minus the 72 is going to give me E1 of 18. All right, same calculation. Instead of 12s, I get 24s. Oops, hit the wrong button. 24, so that's 180. So E2 is equal to 180 minus 72, which is 108. So X is going to be equal to 18 times 24 minus 108 times 12 over 18 minus 108. I'll just crunch that all in one shot. 18 times 24 minus 108 times 12 divided, oops, not dividing enough, so let me close parentheses, then divide. 18 minus 108, and I get 9.6, which happens to be the correct answer. All right, and that would be the solution to that equation. All right. The optional topic, optional meaning I wouldn't put anything like this on an exam, but you might be curious, are there more complicated questions? So you could do it with more complicated problems. The only difference is what you would select in your guess. All right. What we want to do is select convenient values for the value of X, but it's not as simple as being like, okay, well, just take a multiple of the denominator. So in a lot of ways, it could be trial and error, right? So, you just got to sort of bear with it. But one thing that you could use is a second guess would be your first guess plus whatever the least common multiple is of the denominators, right? So the least common multiple of 4 and 6 would be 12. That would be the smallest number that could be divided by both 4 and 6. All right. A common multiple that you could use, it doesn't have to be the least, would be just the product of the two denominators. So if I did 4 times 6, I would get 24. That would also work. But if I, just for convenience, I would take the least common multiple. All right. So I'd hang on to that number, find a value that would work for the first guess. So if I try plugging in a 1, 5 times 1 plus 13 is 18, which is not divisible by 4. All right, 5 times 2, 10 plus 13, 23, not divisible by 4. If I plug in an X value of 3, 15 plus 13 is 18, it was 18, geez. 28 divided by 4 is 7. So that one works. I would check it over here. 7 times 3, 21, plus 9 is 30 divided by 6. That checks out. So I would let my first guess be equal to 3, and my second guess would be 12 more than that, because that's my LCM. So that would be 15. And I can verify that because if I plug in a 15, all right, so 5 times 15, 5 times 15 plus 13 gives me 88 divided by 4 is a clean number. All I care about is it being clean. All right, so you could verify, I can leave that stuff there. All right, you can verify in both cases just to make sure. We need to do the calculations anyway. So I keep hitting the answer button for some reason. 7 times 15 plus 9. 114 divided by 6, that checks out. It gives you a 19. All right, so those would be my values that I would use. All right, so I'd plug in my 3 to the entire left-hand side. All right, LHS. Sorry, I don't know why I did the H part first. All right, and then we follow the same process for finding E, RHS. All right, so like I did at some point, I forget, I'll write the expression here so I can just kind of zoom in. So 5x plus 13 over 4 plus 7x plus 9 over 6. All right, so I'm going to plug in the 3 first. So plugging in the 3 first gives me 28 over 4, which is 7. 21 plus 9 gives me 30 divided by 6 is 5. And then I subtract off the right-hand side, which was 11. So that's going to give me a 1. I don't think I needed to slide this as far over, and I don't know why I labeled it G1. Gotta love it. All right, so my E2, I'm going to plug in a 15. All right, if I plug in a 15, I get, we figured this out before, it's written up here, it's going to give me a 22. And then a 19, that happens to still be up on my calculator screen, so I'm going to take advantage of that. And again, subtract off the 11. So that should be, I believe, a 30. 22 plus 19 is 41, minus 11 is 30. So my x value is going to be my E1 times my G2 minus my E2 times my G1 over E1 minus E2. So 15 minus 90 over negative 29. That's lovely. 15 minus 90, negative 75 over negative 29. 29, I believe, is prime number. I don't think we're going to be able to simplify this except to go into a mixed number. You pop it in. Yeah, it's going straight to decimal form here, so I would probably just leave it as 75 over 29. All right? If the directions tell you to round it in some way, you could. But yeah, let's see, 2.59. So the textbook went to 2 decimal places, but I would just leave it as the fraction form. So x would be equal to 75 over 29. All right. So that's probably as tricky as it could get, but you know it's still based on the same concept. All right, so now you should be able to try 3.1.2, and again, if you want to practice with the optional section, that's great. It's not something I'm going to put on the midterm or the final exam. So I would focus on the first set, numbers 1 through 10. But you know, if you want to challenge yourself, then obviously you can go for the optional stuff too.